Well, thank you for coming. As my title says, I'll be speaking about Mars atmospheric in situ resource utilization projects at the Kennedy Space Center. I'm a research chemist at KSC. I've been there for 9 years, and much of that time been spent working on ISRU. And so let's get going. So quickly, I'll speak about the projects and the team members, what are the Martian resources, some of which you saw this morning, which covers a lot of the territory I'll refer to briefly. I'll talk about the Mars atmospheric processing module, Mars propellant production with ionic liquids, and a self-cleaning boudoir reactor for full oxygen recovery, and some conclusions. And so here are the various people who have been working on these projects, Mars atmospheric processing module, Paul Hensey, Andy Meyer, John Bayless, Ionic Liquids, again, Paul, Tracy Gibson, Jan Surma, Laurel Carr, and Steve Paley are at Marshall, and Matt Marone at Mercer University in Georgia. And self-cleaning boudoir reactor is, again, Paul and Andy, and John and Tracy, Jim Captain, Griffin Lund, Bobby DeVore, Matt Mansell of Marshall, and Mark Bergman of Pioneer Astronautics. So Mars, as you heard this morning, has lots of resources. The atmosphere's about 95% carbon dioxide, and that's the part we're most interested in, using that to make propellant. And then also there are significant amounts of water. Again, as you saw this morning, the graph on the upper right there shows water coming off as a function of temperature. And that adds up to about 2% water in the regolith virtually everywhere you go on Mars, and higher concentrations in other places. So that's very useful. And even up to 10%, even equatorial regions have some of those areas in blue down here in the lower right. Those start approaching 10% water, even where you would think it would be least likely. The ground truth from Curiosity shows that it's somewhere between 1.5 and 3% water in the regolith. I'd average the dynamic albedo of neutrons experiment shows an average of around 3% water and up to 7% down 40 centimeters in some locations where Curiosity is explored. And then they've also predicted there's transient liquid water between the granules in the soil in the top 5 centimeters of regolith. I don't know whether that's practical, but it's very interesting to see that liquid water can exist on Mars at the surface, but briefly, at the right temperature. So for several years, I've been speaking here about the Marco Polo project, which is about in situ resource production of propellant. And obviously, you could do it as a Mars sample return to demonstrate that and to reduce the risk for human mission projects, start on a smaller scale or a subscale module that would show that you can do this. Marco Polo stands for Mars Atmospheric and Regolith Collector Processor for lander operations, and we got started about 5 years ago. And the atmospheric processing module I'll be calling the APM. It freezes, has two main functions. It freezes the CO2 from a simulated Martian atmosphere in our system, and has a Sabatier subsystem, which is a methanation, which is what Robert uses in the Mars Direct, and which is what we'll be using for this process. Excuse me. And then there are other modules. In order to get the water out of the regolith, we'll have to mine it, extract it by heating, purify that water, and electrolyze it to hydrogen and oxygen. Send the hydrogen to the Sabatier system, be combined with carbon dioxide, and then we'll liquefy the methane and oxygen that's produced. And this is an early stage concept of what the lander would look like for the Marco Polo project. And I'll be speaking about the atmospheric processing module up in the upper left there. And then the other modules are there as well. We also have now at the Kennedy Space Center, we have the water cleanup module in the center there. That was at JSC for quite a while. So what are the goals? We were assigned to the ability to collect at least 88 grams of carbon dioxide an hour to be able to supply the Sabatier reactor. We simulate the Martian atmosphere around 10 millibar or so with a mixture of carbon dioxide and nitrogen and argon. And then we'll need to supply that at 50 psi to the Sabatier. We'll convert it into 32 grams an hour of methane and 72 grams an hour of water, which is a byproduct of the Sabatier reaction. And then the original plan was to operate it for up to 14 hours a day for several days autonomously with minimal input from controllers. Obviously, we want to minimize the mass and power. We want to fit within the area, the blue box there, the blue trapezoid, I guess is the right word, that shows about how much area we have on the lander. It's about 9,000 square centimeters. We actually built one that's in a rectangular shape, but about the same area. And it's about 44 inches taller, so from the bottom of the platform. And so, the idea would be make 2.2 kilograms of propellant per 14-hour day, which would add up to be sufficient for our sample return mission. And, I forgot to say thanks to Mike Heck this morning for giving me a shout out during his presentation. Our team also lost to his team, but again, hats off for the success and the great progress you've made. And so this adds up to be about 1/6 the scale of what you would need for a human Mars mission. And I won't go through all the details on this because I've shown it before, but basically you've got the atmospheric processing module consists of we get 2 freezers, and they work in an alternating fashion. One is freezing while the other one is supplying CO2 through the Sabatier reactor. We separate the methane and the hydrogen. In our case, we use a membrane, and the membrane would go to a dryer and liquefaction. Then we have a condenser to take the water out, and electrolyze the water would be on another module. So here's a photograph of what we've built. The Sabatier reactor is inside the aluminum foil wrap, which covers the insulation. The gray tube next to that is the membrane module, where we separate the hydrogen from the methane product. And there's a recycle pump down at the bottom there that pulls the material from the membrane module to recycle it back into the Sabatier reactor. In our case, we broke the process in half for the freezing the CO2 because of the limitations with the cryo coolers that we use. They're not able to take the high pressure, so we take the CO2 as it's being formed in a gaseous form and store it in these 2 tanks up top. And the freezers are down in the lower right. You can't see them very well, but have these copper coils around the body of the cryo cooler to take away the heat that's being generated as you freeze the CO2. We developed a heat exchanger that has enough area and good thermal characteristics to freeze the CO2 at the rate we needed. And there's a better picture of the CO2 freezers. And there's a chiller that runs chilled water through those. On Mars, you would use a radiator system of some sort to get rid of the excess heat. We use a Sabatier reactor that's based on one that was developed at Pioneer Astronautics for a different project. The idea is to preheat the carbon dioxide as it's going through the reactor and then take away some of the heat of reaction and then dump some of that to the environment before you send it back in and react it with hydrogen. And so we get a very good conversion, close to 100% in pure methane product there. Here's a table of a series of 7-hour runs, continuous hours on stream, each one, different days, but at least we were showing continuous operations. The first 2, we used just pure CO2 and froze that out to demonstrate that things were working. But the second 2, we used the simulated Mars gas I talked about. We have a vacuum pump that we use to pull on the chambers that we're freezing the CO2 in, that we pull the pressure in that chamber down to simulated Mars pressure. So we're simulating Mars pressure and gas composition, but not the temperature of the gas coming in, but you would have to preheat it. You would have an ability to warm it up a little bit so it didn't cause valves to freeze or anything like that by using the excess heat from other reactions there. So we were freezing on the order of 70 to 80% of the CO2 that's coming into the system. And you have to have a continuous flow of gas through the system because the nitrogen and argon otherwise would pile up around your freezing head and greatly slow and stop the freezing process. So you need gas coming in to sweep that gas away. And in that process, we don't freeze some of the CO2, but it's a necessary part of the process. And for these runs, we're getting around 140 to 160 watts of power required to freeze the CO2 at that rate. And we're actually exceeding the goal of 88 grams an hour, very close to 100 grams an hour. That way, if we have a little leak or something somewhere, we've got some excess. And then the average lift, that term used with cryocoolers, is around 0.2 watts per gram of CO2 per hour. And with our system, a little bit of variation as you scale things up. You've got to make sure that there's good thermal conductivity through your cold head. And we were averaging right on the money at 32 grams an hour of methane and 99.9% pure, except for one run there with the third run. We have only about 96%. We were losing some gas during the manual draining of water from the Sabatier condenser, and that threw off our separation column for a while, so we didn't quite get all the methane. And we're a little shy on the water we're producing. Instead of 72, we're getting in the upper 60s to 70. We've been looking for the water. We haven't found it yet. In the last run, it was only about 3%. There may be some holdup there. It's not in the methane. We measured the relative humidity of the methane, and it was way too low. It was only a very small fraction of that water is coming out in the methane. Again, it may be just held up somewhere. It doesn't seem to be in the membrane module, though. Let's see, next slide. In the left there, I have some of the results from those long duration tests. The first graph is a plot of two functions, the cryocooler, both the temperature of the cryocoolers is on the upper half of that chart. And when it's down to 150 Kelvin, it's right on that line there. And then the power is on the lower half of that first chart. And that has some variation. This cryocooler controls the temperature by cycling at lower and higher power draw. So it doesn't run evenly, it just kind of goes back and forth, and that's why you get this band of power draw. And then down at the bottom there on the left, I don't know if you can see that, but that's an illustration of the temperatures inside the Sabatier reactor. And we like to keep that well below 600 and closer to 500 if possible. So the CO2 freezer subsystem is working very well. As I mentioned, we're getting over our design goal of 88 grams an hour, freezing around 70% of the CO2, fairly efficient there. And we've gotten lots of good data from that. I've been using that data to do designs of much larger systems, assuming, of course, that as you scale up, you'll get a similar efficiency and how much power is required to freeze the CO2. And so that works out to about 680 watts of lift for freezing 3.1 kilograms of carbon dioxide an hour. The Sabatier system is also working very well. The reactor is very efficient. The recycling is working. We had a failure of the recycle pump, but we recently got a replacement, so that's up and running again. And we're getting pure CO2 at the expected rate and somewhere between 3 and 6% of the water is missing. But we'll find it, by golly, one day. So we've done additional testing. We've varied the rate at which we were freezing the CO2. We still get a very high fraction of the CO2 frozen, but it obviously takes more power to do it faster. But again, that's good. The Sabatier reactor has been tested between 0.3 and 1.2 standard liters a minute. CO2, nominal is 0.75 liters a minute. That works okay on the lower end, but when you go a little too fast, the reactor gets too hot, you start damaging the catalyst, you start seeing carbon monoxide in your feed. So we want to make sure we don't get too hot, don't go too fast for the size of the reactor. So we actually did one virtual integrated test with hardware from JSC in May, and the idea there was turns out they weren't available to do live testing, so we used recorded data from their runs with the other modules and compared that with work at our granular materials laboratory, where some sand standing in for regolith was loaded into a hopper that was taken up to the funnel into an oven, and a simulated oven, and held there, and then the valves open. They have dust-resistant valves that operated very well. So we're getting better and better in terms of getting things running together. We'd like to run another test next week. Unfortunately, JSC is not available. Their funding for this work has run out. And they're also talking about actually moving to the next stage, a much larger module, which would be closer to what you would need for a human mission, and testing that in a Mars chamber. But there is applicability to this technology, perhaps to a Red Dragon mission at some point in the not too distant future, and on the Mars Pathfinder that NASA has been talking about, demonstrating ISRU on Mars somewhere in the mid-2020s. So let's switch gears. I think I talked some about this last year, so I'm going to very quickly go over ionic liquids being used as a way to make propellant on Mars. An ionic liquid is an organic salt that can dissolve CO2 at near room temperatures. That is, you have these very large cations and very large anions, and because they're so bulky, they have a hard time freezing. And so you can have something that's actually an ionic material like salt, sodium chloride, but it's liquid either at or not much above room temperature. And these can be tailored to be absorbers of carbon dioxide. And so the reason we're interested in this is, so there's on the left, just count the boxes. So this is what you would do. You would to make propellant, like I just talked about, from CO2 and oxygen from water. I mean hydrogen from water, and so you got multiple processes. Well, if you can absorb the CO2 directly from the Martian atmosphere and then electrolyze it directly in the CO2 to methane and oxygen, you cut out a bunch of steps and save a lot of mass and power. And the reason we think this is feasible, this is some work that's been done a couple of years ago. One ionic liquid there, where I have the red arrow, the pressure there is very similar to what it is on Mars. This is in a partial vacuum, not in the air, but in a vacuum. And so the ionic liquids have strong enough affinity for the CO2 that they can pull it even at low pressures. I mean, room temperature warm enough so that the ionic liquid is still liquid. So we took some ionic liquids that are available in the catalogs, and then at Marshall they made some new ones that were tailored to be more absorptive of CO2. Mercer University and KSC measured how well they absorb CO2, but we were just using 1 atmosphere testing. Measured the electrochemical windows and built some cells and tested it. Well, there are the candidates, and I won't go through that because there's a lot of chemistry, and I don't remember what all the symbols stand for. But the idea is you have these ionic liquids, and then you have a little electrochemical cell that can be tested. And so I code-named the ones from Marshall as AZ1, 2, and 3 because there may be some patentability there. But they all, the AZ number 3 from Marshall was the best at absorbing CO2. Actually had some very good, time's running fast. But the results on number 3 were the best I've seen in terms of how much CO2 per mass of ionic liquid. So that was a nice property. We looked at all the other factors that were needed. Some of these didn't work very well, so we didn't test them with to make methane. We did a couple, we saw a little bit of methane, so this is a challenge that has not been resolved so far. But at least we made the first steps. And there are other people working on this as well. So I'm going to switch gears once again to the self-cleaning boudoir reactor for oxygen recovery. This is an ECLIS application that is, Jürgen just talked about, the astronauts generate carbon dioxide and you want to be able to recycle that. Well, on the ISS, there's a Sabatier reactor, like I just talked about, that takes CO2 from the system that removes it from the air and reacts it with hydrogen to make methane and water, and the water gets electrolyzed, and you make oxygen out of it. Well, that and that hydrogen then is recycled back in to make more methane. However, on the ISS, they just vent the methane to space, and so that hydrogen that goes with it is lost. And so the source of hydrogen ultimately is from the cargo shipments that come up from the Earth with carrying water to be converted to oxygen by electrolysis. So they only have enough hydrogen to get about half the oxygen out of the CO2 that's in the atmosphere there. There was a call for proposals, which is listed there at the top, and they want to get at least 75% recovery for deep space missions, Mars especially. And so we had a joint proposal from KSC, Florida Tech, Orbitech, and Pioneer Astronautics. We didn't select it, but we ranked high enough, and we got some funding from Kennedy Space Center under the Center Innovation Fund. So what we proposed and demonstrated is to break what's called the Bosch reaction into 2 parts, to make first carbon monoxide out of the CO2 by reacting it with hydrogen, called the reverse water gas shift reaction. And then the carbon monoxide is reacted with itself to make carbon and CO2. The CO2 goes back to RWGS to get the water. And so at the end of the day, you get essentially all the oxygen out. So we built a reactor, and the idea, normally in the past, steel wool has been used, but those reactors clog up with the carbon deposition, and so you have to keep swapping out these cartridges. Well, we had the idea maybe we can clean it out as you go, and there's the test stand we built. We had 1-inch and 2-inch reactors, and here are the internal components there. We have these rotating brushes that are made of steel, and so they're catalytic, and the boudoir reaction, they get carbon deposited them, but because they're rotating and up against rods, some of that carbon is getting knocked off. We tested that, and here's the results. The 1-inch reactor went up to 50% conversion to carbon dioxide and carbon, and we got about 1/4 of the carbon coming out the bottom of the reactor, and that was good. And we also used a larger reactor, a 2-inch ID reactor. It didn't go up as fast, but it lasted much longer and got up to around 76%. Both of them averaged around 40% conversion. And Each one of these 2-inch reactors is equivalent to about 0.6 of a crew person. So you would need 7 or 8 of those 2-inch reactors. We're thinking of scaling them up as well. And so what can you do with this? The idea is you can actually use the carbon as a resource as well. You can filter the air and water. You could throw it into plastics and make more bulk out of your 3D printer material. Throw it up on the wall as radiation shielding, lubrication, carbothermal or electrochemical reduction from metals. You might, if you want to make diamonds out of it, you've got something. And at some point, maybe you want to take carbon dioxide out of the Martian atmosphere, convert it into carbon, and ultimately oxygen. The carbon darkens the surface, and it gets warmer. And releases more carbon from the polar caps. So in summary, so we're developing low and mid TRL ISRU technologies. We've made lots of progress on the atmospheric processing module and broke some ground on electrolyzing CO2 and water in ionic liquids. We've got a graduate fellow here, at KSC who's working on similar work right now. And we got very encouraging results on the self-cleaning boudoir reactor. And I guess I'm out of time. Thank you. Robert.
I was curious, what catalyst are you using in the Sabatier?
What? I'm sorry.
What catalyst are you using in the Sabatier state?
It's a ruthenium on alumina catalyst, 0.5%.
Its characteristic turnover frequency?
I don't know that number offhand. It works as the is the basic thing for me. It does the job. Jürgen was saying.
What interests me is, how are you obtaining the water from the soil? Are these big earth type of works that have to be done?
Well, the work at the Granular Materials Research and Regolith Operations Laboratory, which is another building next to ours, they have something called the Razor Rover, and I guess I've got a little photograph.
Oh, a special rover.
Yeah, it has bucket drum excavators on both ends. That way you can dig on both ends, and it doesn't have to have a lot of mass to hold itself in place. You can counteract the forces of digging with each other. And so then those can be lifted up off, and then you drive to wherever you dump it, and then come back and get more. And it's very efficient. Right.
Thank you.
Okay, thanks. Let's see.